Good morning, everybody. Welcome to day 2 of Organometallics. First, we'll start with just some administrative announcements. So last time we had said, I encouraged everyone to sign in using the physical sign-in sheet, and we're just not going to do that anymore. We're going to take attendance based on the TAs will take attendance since I think now we're familiar with everybody in the class. So no need to do that. If you're looking for the sign-in sheet, you didn't miss it. We're not going to do that anymore. Were there any additional announcements you wanted to make, Wenji, Annabelle?
I think just that's the UCSD crystallography visiting us on this Friday. So if you're interested in how they're solving your crystals, like how they pick crystals, how they mount stuff, I think they'll demonstrate it here. So if you're interested, just come to the Engle lab at 162. There's a microscope. They're going to be there.
Great. And if crystallography piques your interest and you're a first-year student, I would encourage you to check out the other class I run, which is Computational and Analytical Tools for Chemists, where we actually do a site visit to the crystallography core there and have the chance to run and solve samples on the fly. Were there any questions from last time? Okay, in terms of where we left off, we had covered structure and bonding. After a quick primer of strong inference, we covered structure and bonding of main group organometallics. And the theme that we were building on was one of complex speciation, multinuclearity, and the implications of some of that structural complexity in terms of reactivity. We're going to pick up right where we left off and delve into wrapping up the last couple minutes of notes on main group organometallics focused on organoaluminum compounds. Let me close the door so there's a little less ambient noise. And I'll go through this pretty quickly. There is a nice handout summary of reactivity of organoaluminums that you should have received last time as a printout. It's also in Canvas, so check that out as a primer if you're interested to read more. In terms of structure, again, one of the themes that we see here are things are not as simple as you're originally taught. And so let's take the case of trimethylaluminum. When we write this out, when we're learning about its function and reactivity, as undergraduate students, we draw it as Al1Me3. In reality and solution in the solid state, this is a bimetallic adduct. And whereas at first glance, this notion of carbon forming 5 covalent bonds may make you uncomfortable, if as one of the first principles we learn is in organic chemistry is to be uncomfortable with so-called Texas carbons, pentacoordinate carbon atoms. In this case, if we look into the details, this is allowed because the type of bonding at play is a 3-center 2-electron bond. So across these 2 bonds, there's only a net of 2 electrons. I have, and so the molecular orbital depiction in simplified form is shown on the right of this slide. And I think you'll be familiar with these types of 3-center 2-electron bonds from other examples that we covered already and from adducts like borane that you may have already encountered in your chemistry career. I have shown here some key bond metrics drawn from the X-ray crystallography experiments, so you can get a sense of not only the structure and bonding, but the distortion from ideality involved in these types of adducts. So if we zoom in on the bridging methyl group here, we see that significant distortion from what you would expect in an sp3 hybridized carbon atom, and significant bond compression to the tune of about 75 degrees. There's also some evidence in terms of short contact between the two aluminums, suggesting there may be some attractive bonding interactions at play that stabilize the overall bimetallic atom. We'll talk more about common modes of reactivity, but one general point I'll make is that that's relevant to the history of main group organometallic complexes is that organoaluminums exhibit significantly attenuated reactivity in ethereal solvents. And if you remember back to the last lecture, we see that ether, THF, 2-methyl THF, these are ubiquitous in organolithium and organomagnesium chemistry. So in terms of the historical development of this field, when people were first exploring organoaluminums, they weren't really impressed by what they saw because a lot of those initial pilot experiments based on the common benchmarking in ethereal solvents did not look particularly promising. It was only when switching to other solvents that reactivity was turned on, so to speak, and the full breadth of reactivity came to be appreciated of organoaluminums. Let me just pause to make one more comment on the bonding depiction. Again, I had mentioned the molecular orbital depiction, and if it's helpful to you, if you are comfortable operating in the P block, then there's a direct analogy here with the structures that one encounters in 1,2 carbocation rearrangements. Where these types of three-centered 2-electron bonding interactions are encountered as transition state structures. Few more examples here. So here's, yes. Oh, thanks.
I was just wondering, the ethereal solvents, maybe I just missed it, but what was the explanation for why the reactivity is attenuated?
Let me come back to this point when we talk about the mechanism, because I think it might be more obvious. But just to comment very briefly, the first step based on kinetic data and now common understanding, the first step for a reaction to take place is these bridged organoaluminums need to dissociate to their monometallic state and then react. And so ethereal solvents, you can imagine if one of the key events that needs to happen is to create an open coordination site, then that can be more challenging in ethereal solvents.
Okay.
Coordinating character.
Thank you.
Yep. Another example here, triphenyl aluminum, or more precisely, hexaphenyl dialuminum. Similar bonding motif here, isostructural with the exception of now the bridging atom, which again, as a refresher, we define using the Greek letter mu with superscript 2, mu2. Phenyl group here is sp2 hybridized. We know that sp2 hybridized carbon atom would ideally have 120-degree CC angle, and you see significant distortion here, reflecting the nature of the bonding interactions at play. reactivity, again, I'm only going to spend a couple minutes on this just because we have the handout that describes the breadth of reactivity of organoaluminums. But we can bring this back as a jumping off point, though, we can bring this back to the point that I made earlier about first principles being your guide. And by first principles, again, I mean electronegativity. We talked about in last class how electronegativity can be viewed as a readout of orbital energies. Highly electronegative atoms like to hold their electrons in low energy orbitals. Electropositive atoms hold their electrons in higher energy orbitals. And the readout then of the electronegativities within a carbon metal bond can give you a sense of how covalent or ionic that interaction is. That's a theme we'll see again and again. Helps you rationalize main group element, organometallic reactivity, helps you rationalize organotransition metal reactivity, helps rationalize when you're going from a so-called early transition metal to a mid transition metal to a late transition metal, again and again. So one thing that we can quickly appreciate consulting the values that I showed last time is that aluminum is a more electronegative atom than either lithium or magnesium. As a result, the carbon metal bond has more covalent character, which is not to say that it is covalent. Certainly, aluminum is much more electropositive than, say, palladium, but it is more covalent. And so, whereas organolithiums and magnesiums, as we know, have high reactivity with polar functional groups, organoaluminums can now react with less polar functional groups, namely alkenes and alkynes. We talked about this elementary step of carbometallation, or in the specific case of organoaluminums, carboalumination. Now, Eugene foreshadowed the point that I'll make next, which is one about mechanism. So the first point in terms of the stereoelectronic elements of this process is that it is syn stereospecific in its initial reaction. Now, carbometallizations, including carboaluminations, can, in the net, be anti-selective because there are secondary processes involved. But in the initial addition, these are mechanistically defined to be syn stereospecific. And then you need to play some tricks if you want to achieve an overall anti-addition outcome, and those are well documented in the literature. But the initial addition is syn. Hopefully you understand that from the mechanism. What can we learn from what about the underlying details of how we go from bimetallic to monometallic and then ultimately to the reaction in question, and what are the consequences, or how does that reflect in terms of the overall rate law? So let's dig into that. First, going from the bimetallic adduct, the initial step is a reversible dissociation from bimetallic to the more reactive monometallic form, which you can appreciate has an open coordination site. Throughout the course, we'll refer to open coordination sites using this nomenclature of a square, very sophisticated, I know. And then from this open coordination site, a pi bond can coordinate. In this case, it's drawn as a monosubstituted olefin. Upon this interaction, which is the rate limiting step, we form a new carbon aluminum bond and develop carbocation character in the at the more thermodynamically favored position, which in this case is secondary. That sets the stage for the alkyl shift, and then the overall process is addition of a carbogenic group, in this case ethyl, and the metallic group, in this case aluminum, across the olefin. So given this mechanism, what might we expect the rate law to look like? I can ask for well, maybe I'll just ask if there's a volunteer. So we're still in mental warm-up stage. Any volunteers? Yeah, Alex?
So then the rate law would be A times concentration of olefin times concentration of the trialuminum monomer.
So olefin maybe I'll draw this out the way it's drawn up above, just to make it clear. And then okay, is that correct?
I mean,
Is that what you said, or did you say something different?
what it would be the triethyl aluminum monomer, like
Okay.
directly from the rate determining step, and then
So how would that
you can
reflect?
express that in terms of the dialuminum like hexaethyl dialuminum with the pre-equilibrium.
Okay, and what would that look like in terms of the exponent?
Guess to the 1/2.
Perfect. So half order. And you can help yourself to a starburst if you, I think we're gonna try to throw starbursts at people and hope for the best. Or pass them. Annabelle's not as aggressive as I am. Okay, so first order in olefin, half order in aluminum. Oops, I'm sorry. And then let's look at relative reactivities of different olefin substitution patterns based on the mechanistic manifold that we are discussing. So there's a couple different things at play. I mean, you could rationalize potentially, based on the information provided so far, you could come up with different orderings potentially here. But does anyone want to hazard a guess on how you might expect different substitute olefins to react? Yeah.
I would expect ethylene to react the fastest. And,
Okay, why is that?
it's the least sterically hindered.
Okay. Then what?
Mono substituted after that.
Okay.
Di substituted, with both on one side of the olefin after that, and then
Okay, drawn suggestively left to right in the order that they indeed react. Very good. And so sterics is a dominant factor here, and you can imagine if indeed this is the rate determining step, if initially we're forming this metal high olefin atom. Okay, maybe that's why we pass and then that step is going to be, that event is going to be very sensitive to sterics. Very good. Okay, an application of carboalumination in the real world comes from, one of the classical examples comes from the work of Carl Ziegler at the MPI for Polenforschung, called the COFO for short, where I spent a postbac year after undergrad. And the key commercially transformative process here is referred to as the Aufbau process, so-called building up molecular complexity, where carboalumination across ethylene repeatedly enables controlled oligomerization or polymerization. The carbon aluminum bonds are ultimately quenched with O2 and an oxidative workup, leading to primary alcohols, which I think all have appreciation for their utility as surfactants, among other potential applications. Okay, so that wraps up our brief tour of the main group. Are there any questions before we transition to other aspects of coordination?
So following up on Eugene's question about the mechanism, so if you have an ethereal solvent, what part of the mechanism does the ethereal solvent play a role?
What would you predict?
Is it
The oxygen lone pair that
has the positive charge?
is of that.
That is reasonable, but remember, let's just think about what was the rate determining step? What was that event? It was
Yeah.
addition of the alkene to the unfilled E orbital of the trialkyl aluminum. So one might imagine that with a ethereal solvent that has some level of Lewis basic character, I mean, at a high level, this is all Lewis acid, Lewis base chemistry. So if you're critically reliant on the Lewis acidity of the metal in a potentially Lewis basic solvent, that is going to be a challenge.
Would the same then be true for alcoholic solvents?
Yeah, but there you have the added challenge of you're just going to destroy your carbon aluminum bond because those carbogenic fragments are sufficiently Bronsted basic that they can also just grab a proton from the alcohol. So I wouldn't recommend. I mean, you could do this experiment upstairs, but what floor are you guys on? Yeah, you're far enough upstairs where we'd be safe to add a bunch of trimethyl aluminum into methanol or something. I wouldn't recommend it, but you can see what happens, and I think you'll find it's pretty robust reaction. Okay, thanks for those questions. As I can't emphasize enough, my philosophy for any grad class is this should just be maximally interactive. Like there's stuff that we want to cover, but the most important thing is to ask questions, answer questions, explore things you're interested in. Okay, so we kickstart the coordination chemistry section of the class with the problem of the day to get your creative juices flowing. And so I'll read that here and then I'll switch back to the iPad, and this can be, I think this can be fast and furious. So just as you come up with ideas, let's throw them out there and get an open discussion going. Cobalt-3 coordination complexes play a very important role in the historical development of the field of coordination chemistry, as well as ultimately the field of organometallic chemistry. These are termed Werner complexes, which is an ambiguous term. I think what is and isn't a Werner complex is not totally clear even to me, but typically there are these cobalt-3 complexes with some combination of simple ligands, water, ammonia, chloride, et cetera. And the question here asks you to provide the 3D structure, but I'll generalize this to say, provide as many plausible 3D structures just based on that molecular formula and not, I'm going to task you here to be a time traveler. Think back to the 1900s, the 1910s, and what is and isn't known. And so if all you have is this molecular formula and no other knowledge or 100 years of literature, what things might you be tempted to draw? And then what experiments might you be able to do to distinguish among those possibilities? This is somewhat of an unusual exercise because we don't often put ourselves in the position of the scientists, the chemists actually working at the time and what tools are available to them, what knowledge they had. But I think it's useful here as a kickstart of this discussion, which has a historical angle to it. I managed to do something I shouldn't have. All right, so let's get some ideas written down. What did I do here? Okay, sorry. There we go. We're back. All right, Amy, what do you think?
The first one that I have is just octahedral cobalt with I just had 2 chlorines on it.
Yeah.
Like on the, I guess, on like the
I'll
axial.
draw one here. Where do you want to
Sure,
draw that?
trans to it.
And then, your 4 means around the other positions. And then your final chlorine,
Should be an H3.
yeah. And then your final chlorine, I just have the outer sphere as a,
Okay. What do we think? Do people like this? What else is reasonable to draw? And you mentioned trans, so just for completeness, we can say, again, based on the information that's provided, we have no reason to draw it trans and not to draw it cis, so that would be another plausible possibility here. Good. What else? I'm surely lots of other possibilities people came up with. The weirder and wackier, the better. What do we think? Riku, do you have anything else she came up with?
Yeah, this might sound really absurd, but can you have bridging chlorine? So have like
What would it bridge?
so they would have like how to explain it? A chlorine that's central chlorine that's connected to and like
Oh, I see.
and
Yeah, okay, so this is, let me think about this. So it's if I understand you correctly, you're thinking about something that's gonna be like in some infinite coordination complex, potentially. Is interesting to think about. So it's gonna be like this. And then this is gonna be overall no, that will be charge neutral. And then you'll have one outer per metal, you'll have one outer sphere ammonia as a co-crystallized. Yeah, Alex.
Just have all the ligands bound to them.
All the ligands bound to metal, sure, that's reasonable. I'm just gonna draw this. How many are there? There's 7. Something like that. Then there's other possibilities that I think maybe you came up with, like you could have 4 ligands bound and 3 not bound, 5 ligands bound, 2 not bound, or possibilities like this. Any other possibilities?
Trigonal antiprismatic geometry.
Trigonal anti-prismatic, would that still fall within a 7 coordinate?
Oh, that's 6.
Oh, I see.
Or you can trap it for 7.
Okay, so a version of this that is distorted from octahedral, something. Okay, that's reasonable. Well, believe it or not, these are all good suggestions. So believe it or not, one of the common prevailing proposals at the time was something that looked like this. And again, there's different variations on what I'm going to draw, and all of them look equally crazy by today's standards. This is now affectionately referred to as the Chattanooga choo-choo representation of the complex, because it has this like long tail that looks like a choo-choo train. Why were people in the 1900s attracted to this type of connectivity? It had to do with this prevailing belief or intuition that valency and coordination number should be equivalent. So at the time, it was very quick and reliable to establish molecular formula through things like flame tests and thermogravimetric analysis, or that era's form of thermogravimetric analysis. But X-ray crystallography, remember, was single crystal X-ray crystallography was not online at this point. So coming up with 3D structures was more challenging. And it might stand to reason, if you know that something is formally +3, that it should have 3 anionic groups around it. And it was through the work of Alfred Werner and ultimately through this appreciation of stereochemistry that that two different complexes with identical molecular formulas could in fact be chemically distinct, physically distinct, and that phenomenon is most consistent with octahedral geometry that allows for cis-trans isomerism. And I would say that make that comment generally, and you can imagine that to actually use that as a confident form of proof, you need to look at many different variants, different ligand environments, some chelated, some not chelated, et cetera. But stereochemistry was a very important tool in advancing these basic concepts of coordination chemistry, ultimately winning Werner the Nobel Prize in 1913. And the dogma that it really, you can think of this as he won this Nobel Prize for overcoming this dogma that the oxidation state and coordination number needed to be identical. So now we call these octahedral cobalt, or in some cases nickel complexes, Werner complexes. A quick point about the nomenclature here, because I think if you are a practitioner of this field, it becomes intuitive to you, but if you're seeing this for the first time, I don't necessarily think it's intuitive, which is we use this Pythagorean geometry nomenclature system. And the naming is based on the number of faces, not the number of vertices. And that makes sense, I think, if you think about the overall 3D structure, but can be confusing at first glance if you think octahedral, octa, shouldn't that denote 6 ligands, i.e. 6 vertices? No, it's based on the faces, which have no real chemical meaning other than their connection to this Pythagorean ideal. And the same goes, and sometimes, and I think what can make it confusing is sometimes these coincide. So tetrahedral geometry, for example, the number of faces and the number of vertices is the same. Okay, some other nomenclature or shorthand that you might see in the literature. This is really just to provide a guide as you navigate papers that might be relevant to your research. We tend to, for those of us working in organometallic catalysis, we often like to express uncertainty by this type of nomenclature. So we would talk about a generic complex using generic M. We would talk about an unspecified number of ligands using this subscript N, and unspecified ligand identity using generic L. So you might encounter, I mean, you could go to JAX or Angevante or pick your favorite journal and probably find an example where a catalytic cycle for a cross coupling begins the initial intermediate in the cycle is something like this. And that's basically saying we don't know exactly what the coordination environment is, but we know that it's in the zero oxidation state. And we know it has some number of neutral donor ligands on it. Other terminology that you might hear would include aqua complexes, which are those that have at least one water, in some cases multiple waters as ligand. We'll talk about carbonyl complexes, which are complexes that have CO specifically as the ligand. And one of the things you can quickly get an appreciation for is we talk about electronegativity, and now here we have ligands with very different electronegativities, oxygen versus carbon, and different intrinsic ability of forming covalent bonding interactions. So you could imagine, this is a vast oversimplification, but you can imagine a metal bond to oxygen is going to have more ionic character, again, at first, vast generalization compared to a metal bonded to carbon. An important concept that we've already touched on a few times, but I'll just formalize here, and this will come up again and again in the class, of central importance to some of the research that my group does. This is the concept of chelation. This comes from the Greek root for claw or crab. Chelating ligands are those that, just like a claw, can bite into the metal at multiple, through multiple distinct non-contiguous atoms. And so example chelating ligands are some that you will have already encountered in your research, like BIPI or TERPI. Chelating ligands that have not two, but actually three coordination sites have a special name, because we like to give names to everything, which is, we call them pincer. In this case, it would be an N pincer. And I think the nomenclature here, it seems like it would come from pinching, but it actually comes from this military maneuver called pincer maneuver. And then we like to give names, like you'll hear names like piano stool, these with three different chelating ligands we call paddle wheel complexes. Point is not necessarily to remember all of this, but just so that you have some general orientation about how organometallic and inorganic chemists like to communicate to each other. Probably if there's a single point about chelation that I could leave you with, it is the importance of the thermodynamic consequences of chelation versus non-chelation. So this can be tested experimentally. So here we have a model reaction displacing ammonia with diaminoethane. And this, of course, the equilibrium, this is in principle an reversible reaction. The equilibrium lies far, far to the right. If anyone has to hazard a guess, how much is this worth in terms of the KEQ? I'll give you a hint that it is more than an order of magnitude. Al, what do you think? Could you hazard a guess?
1,000.
1,000, so 10 to the 3. You're not far off. It's each chelating interaction, and they're as just a kind of back of the envelope, you can say they're additive. That's not entirely true, but each chelating interaction gives you about 10 to the 5 in terms of KEQ. So you can imagine when I say this lies to the right, it really lies far, far to the right. And to stay with you, Al, would you think that the contribution here is primarily enthalpic or primarily entropic?
I think isn't it both, in that you have a strong bidentate chelator and at the same time you release ammonia, 6 molecules of ammonia.
Maybe let me rephrase this. At least in the example given, would you say like the diamine ligand is significantly more strongly coordinating than the liberated ammonias? That would be the enthalpic contributor. In this case, we'd say they're similar. I mean, not exactly the same, but similar. And so the primary, most of this 5 orders of magnitude comes from the entropic aspect. And so that manifests itself in kind of two forms and flavors. One is that if you just count the number of molecules, that you're generating more free molecules, more distinct molecules when you displace a non-chelating ligand with a chelating ligand. And then the other is you have this rigidity effect of the conformational restriction effect of having the chelated ligand on the middle. We talk about the descriptor we use for chelation is another Greek letter, kappa, and kappa is defined as the number of single ligating non-contiguous atoms of a polyatomic ligand to a coordination center. So we can just do this quickly and say this ene ligand is kappa 2, bippy would be kappa 2, terpy would be kappa 3. In asymmetric catalysis, chelating ligands have played a very central role because they provide these well-defined, well-differentiated quadrants, such as Noyori's beautiful C2 symmetric atrope isomeric ligand binap, for which he won the Nobel Prize. Many of you will probably already use this in your search at some point. And then in everyday life, we encounter the phenomenon of chelation quite commonly, and the way we encounter it most commonly, besides the chelating events happening in our body, is probably in terms of man-made interactions, that of EDTA, which has uses as many uses, but water softener, metal scavenger, food preservative, an additive for buffers, and so forth. And you can, yeah, you can.
Sorry, could you go back to kappa and explain what you were saying? You said non-contiguous, sorry, I think I just missed it.
Yes, this will be, I think this might be more clear when we talk about eta, the difference between eta and kappa. So kappa is basically just the number of coordination sites that a given ligand has. That's the simple way to.
So like binap would be 2.
Binap would be 2, yeah. And so we can play this out, and so EDTA, for example, if we assume the carboxylate is each giving 1, and carboxylates are complicated because they themselves can sometimes coordinate kappa 1, sometimes coordinate kappa 2. So we wouldn't know just from how I have this drawn, is each carboxylate kappa 1 or kappa 2. But let's say each is kappa 1, and we've got 1, 2, 3, 4, and then the 2 nitrogen ligands. So this would be kappa 6. So part of the utility of EDTA stems from the fact that it's very simple and kind of like relatively benign chelator, but has the capability of being highly polydentate.
You're saying each of the nitrogens are accessing a coordination site as well as each of the carboxylates?
Yes.
Okay.
And so another term that's related to chelation and is kind of in some ways equivalent is denticity. Greek root here is the same as that in dentist, so teeth, biting down, and so you'll hear things like monodentate, i.e. kappa 1, bidentate, i.e. kappa 2, etc. Okay, we'll take now a historical tour of some of the origins of this field. And we'll try to cover the better part of 2 centuries of research in about 30 minutes or so. So buckle in. The first, I think now retrospectively, what's credited as the first well-defined, man-made organometallic complex that resembles the types of complexes we work on today is Zeiss's salt, discovered by William Zeiss, a pharmacist working in Copenhagen. And so it's interesting to think that if I were a researcher, I was pursuing my passions in the 1800s, I'd be working at the equivalent of CVS, but doing organometallic chemistry. And to this day, it's not really clear to me why on earth Zeiss would have been doing this, but what he was doing was refluxing this platinum salt that he happened to have on hand. And maybe the origin of this is, of course, we know that platinum salts have a very important role in modern cancer biology, but have, I think, a historical role as in medicine. So he was running this experiment to take platinum, heat it up in ethanol, and what he retrieved out was quite a surprise, a yellow tinged salt that seemed to be air stable. And for the life of him, he couldn't figure out what this was. Again, same theme, you could very quickly determine the molecular formula through techniques available at the time. Maybe not so quickly, but you could, with some work, determine the molecular formula. But then how all these atoms fit together in a 3D constellation was not immediately evident, because the types of bonding interactions at play would never been documented in human history up until that point. It took more than a century, and the real nail in the coffin was a crystal structure that came in the 1960s to ultimately establish the connectivity and bonding depiction that we have shown here. And the key bonding interaction that sparked and propelled the field of coordination chemistry, organometallic chemistry forward was this interesting pi bonding interaction, where a pi olefin metal bonding interaction, where the filled pi bonding orbital of ethylene is donating electron density into an unoccupied d orbital around the metal. And this has a bonding component, and as we'll talk about when we zoom into the molecular orbital depiction, a back bonding depiction where filled d orbital on the metal kicks electron density into the pi star antibonding orbital of the olefin. And this is now referred to as the Dewar-Chat-Duncanson coordination model for olefins and metals. Some great historical accounts here that we'll add to the readings folder in case this piques your interest and just want to understand more about the historical origins of this particular line of inquiry in this field in general. Contemporaneous to some of this was the work with main group organometallics, particularly Grignard reagents, that netted Grignard Nobel Prize in 1912. And I won't say more about that because we covered that in day one. Here's an early review if you want to see kind of a historical perspective on that. It's interesting to kind of connect different research threads at Scripps. And so organometallic chemistry also has this interesting interplay with medicine and human health. So we talked about platinum complexes briefly and how those play a role in a modern form of cancer treatment. But further back, the advent of this first modern antimicrobial agent as treatment for syphilis was developed by Paul Ehrlich's group, a molecule called sulvarsine. For those of you who are familiar with the work and career of Paul Ehrlich, he's a Nobel laureate, but not for chemistry, for medicine. And he's credited with developing the concept of the magic bullet. And the origin of this is itself interesting. It comes from a German myth. But the idea is that for certain types of pathogenic infections, so take a bacterial infection, for example, you have this challenge of differentiating human cells and foreign cells. And so the idea of a magic bullet is that you have this molecular entity that, like magic, can navigate and distinguish between what is human and what is pathogenic and attack i.e. shoot only the pathogenic, only the pathogen. Now, some of us would see the irony in this, that thinking that an arsenic compound is going to have this type of magic in being able to be so so precisely distinguishing. Of course, organoarsenic compounds have extreme amount of toxicity in general. But indeed, this did work. It worked as a treatment. And there's some interesting nuance tucked in here, which is that despite being used for decades, actually, the structure of salvarsan has remained the topic of some mystery and ongoing investigation in the research. So it was originally defined as shown up here, but based on most recent available data from mass spec, it's actually thought to be a mixture of the Scripps and penta metallic forms. And you can imagine how, using most other analytical techniques, this is actually quite difficult to distinguish. So an interesting example, not the only example, but one of a number of interesting examples where a medicine was used for a long period of time and actually the precise structure was not fully appreciated. All right, that kicks us into another extremely important advance in the history of organometallic chemistry, and that's problem of the day number 2. So let me share that. This is going to be another highly interactive one where I'll need everybody's help. So again, we're going to jump in our time machine. This time, we're going to transport ourselves to the early 1950s and put ourselves in the shoes of 2 researchers, Paulson and Kelly, who attempted to run the experiment shown here, synthesizing this fulvalene complex through actually kind of a modern, and interesting how things come full circle, kind of a modern looking reaction, in this case, an oxidative cross-coupling. Doesn't look unreasonable on paper, but rather than the expected fulvalene adduct, they observed a bright red, crystalline, solid, highly stable, certainly not the fulvalene. And so again, quite quickly, they're able to determine that this mystery product has both organic component and metal component, but the 3D structure remained elusive. So like in the previous question, what I'm asking you to do here is not just think about what the product that we know to be formed here based on, a decade or almost a century's worth of knowledge, but think about all possible products and then using a strong inference workflow, what experiments you might design to distinguish among these possible products. So I'll give you 2 or 3 minutes to brainstorm, compare notes with your neighbor. And again, the goal here should not be to come up with one, but at least try to come up with 3 different connectivities to get the discussion going. Yes, yes. You asking a question? Oh, we'll give another minute or two. All right, so Ichiro, can you give us one? What do you think? Oh, I made you get up? I thought the room was mic'd, sorry, okay.
So iron two complex, bearing two, to ionic ligand.
Okay, could you say that one more time? You didn't come through super clearly. I heard two ion, but I couldn't hear anything else.
So iron two complex.
Iron two complex, okay, I got it. Iron two, and then what are the ligands?
Ionic. Sorry, I forgot the name of this alkyl. From the MGBR reaction.
So what are the ligands you're saying from the Grignard reagent?
Yes. So two Grignard reagent.
Two Grignard reagents, okay, so the groups from the Grignard reagents are coordinating, so, okay, let's draw one of these, so this is good, okay, thanks, Suichiro, so here's the structure we now know to be the winner.
Sorry.
Yeah.
Which? Sure.
Okay. Let's try that again. I had this figured out. Advanced, oh, I see, I clicked the wrong button. Okay, is this what you had in mind, Suichiro?
Yes, exactly.
Oh, okay, good, perfect, thank you. And then I think the other way that we could probably, if we just take Suichiro's suggestion, we say the two ligands from the Grignard get incorporated, then the other way to draw, there are many other ways, but the other kind of most plausible ways to draw that would be like this, or some combination of like one like this, and maybe one that's like this. These are all reasonable based on the information that's provided. Let's get some more. Thank you, Soichiro. You can take a seat. Let's get some other, even more exotic suggestions. Pierre, what do you have?
So you can have. Like the free complex, the
Okay.
I guess ring slip.
Yeah, okay. That's another form of this effectively, but now we're talking about, if I understand what you're saying this is going to be A to 3. Again, if any of this terminology is like you haven't defined what eta 3 is, we will, don't worry. What else? Yeah, yeah.
Can we do this order between two cyclobenzene and then coordinate to iron?
Oh, okay, that's interesting. So let me see. You're making me work here. Now I gotta draw hard stuff. Okay. And then this is gonna be 2. This, and then this is gonna be iron. No, we don't necessarily, and you want 2 of these probably? Or 1 of them? Well, for the molecular formula, it should be 1 of them, something like this. Is that what you have in mind?
But it will never work, I just.
Yeah, I like it. What else?
Can have an ionic complex with 2 cyclopentadiene ligands and 2 chlorides.
Oh, I see. Okay, yeah, so that's like any one of these. Let's take this. But then you're gonna say it's iron 0, iron 4. And then 2 outer sphere chlorides, is that right?
I mean, that is also a possible structure.
Sure, yeah, I mean, that's the exercise, so I'm not trying to be critical, I'm just saying, is this what you were proposing?
I meant iron 2 and 2 chlorides on the iron.
Oh, okay, then where are the CPs?
So it's like a quatercene dichloride structure.
Oh, I see. The chlorides are on iron, not outer sphere.
Yes.
Got it, okay. Yeah. The iron is still +4 oxidation. Okay, good. What else? Yeah, it's not. Let's do one.
Through magic and will, you could imagine maybe opening up one of the CC bonds of cyclopentadiene, making a ferrocycle, and basically having like a spirocyclic, like 2 of these
Yeah.
6-membered rings coming off of
Very-
iron.
I like this idea. It's very creative. This is gonna be. Boy, everyone's putting my drawing skills to the test. Let's get 1, 2, 3, 4, 5. Yeah, something like this, right? Very cool. And then there are other possibilities. I mean, one thing that we didn't, I'll just say, maybe spitball one more that we didn't talk about, but you could imagine based on other stuff we've talked about so far in class is you could have things like this, where you have bridging interactions. We said magnesium likes to bridge. Maybe there's some magnesium in here. Like that. Okay, and then now let's talk about some experimental techniques that could allow you to distinguish among these possibilities. Yeah.
Look at its magnetism.
Magnetism, okay. What specifically are you going to?
Well, it'll tell you if a compound's diamagnetic or paramagnetic, you know the oxidation state on iron, you know how many electrons are being donated by the ligand.
Okay. Okay, what else do we have? Even simpler. Think about, yeah, here, let's keep it simple.
I mean, the color of the complex tells you something.
Color, okay.
But also along those lines, is IR around?
IR is around, NMR is even around, but not
Well,
the power that we're,
You don't need power, you just need to see the symmetry.
okay, beautiful. Amy, did you have something you were?
I can say NMR.
NMR, okay. Anything else that people have in mind here?
Like, try to derivatize it as things reactivity,
Okay.
whether it does EAS or SAR.
Good, okay, so probably based on other points I've made, the first thing that we're gonna do, nobody mentioned, because you probably implicit, would be like a elemental analysis. And the elemental analysis is gonna be useful, because that, right off the bat, is gonna allow you to rule out possibilities that have other elements in them. Or, I mean, again, nobody proposed this, but you could imagine ferrocene or iron with 3 CP ligands. So that would allow you to distinguish among those possibilities. Now, the others are all isomeric. So I think Pierre caught and Amy caught what we were thinking here is that symmetry is going to play a very important role. So you can quickly appreciate that by NMR, you should only have a single CH resonance and a single C13. So you should only have a single proton resonance and a single C13 resonance. For IR, you should have, well, IR is more complicated, but you would have the high level of symmetry would implicate that you're going to have a smaller number of stretching and bending frequencies. So these techniques based on symmetry will allow you to distinguish among most all of these other possibilities. And so, you know, it's not, I think won't come as a surprise to anybody that the winner at the end came out to be this one. So, but this was not the originally proposed structure. So this is an interesting point. The original paper proposed actually this structure shown here, which again is identical in terms of formula weight. And so this, when this publication came out, of course, it created a lot of stir. And if you haven't had this experience yet as a graduate student, you probably will at some point in your career where you see something published and it just makes you very uncomfortable. And you're pretty sure it's wrong, but you're not exactly sure why it's wrong or how it's wrong. You don't know the solution, but you know that it's wrong. And that was the case here. So this high profile publication came out proposing this structure, and immediately the community felt uncomfortable. Why? Because you have effectively a dialkyl iron that has this incredible air stability. And that is unlike any alkyl iron species known at the time or known since. So something seemed off to 2 research groups. And the 2 research groups that chimed in with the structural revision were already well known at the time and then rose to even greater fame. That there was one team out of Harvard led by Jeff Wilkinson and also joined by R.B. Woodward, a giant in structural elucidation, and a team out of Germany led by Fischer, who ultimately in back-to-back papers proposed a structural revision to the metallocene structure that we're now familiar with, ferrocene. This ultimately, and not without some controversy, led to Nobel Prizes for Fischer and Wilkinson. Notably, Woodward was left out of this particular prize, but he certainly got his fair share of recognition over his career. And as you can imagine, the back-to-back nature of these papers sparked a major rivalry between these 2 groups that continued for decades and really defined this era of organometallic chemistry. I'll comment just a moment on the name that became adopted of metallocene. So the scene here is meant to invoke the connection to arenes and aromaticity. So already at this point, it was recognized that these metallocenes have a special stabilizing aromatic nature, again, that was unknown in the literature at that time and now has become a hallmark of these types of coordination complexes. Okay, any questions on that, Amy?
Well, I was just gonna ask, like, what techniques did they use to originally propose that structure? Because it feels like IR NMR would like show you that that's wrong. So like, what were they using?
Yeah, that's a good question. The original authors of the first paper. So they had the elemental analysis. I would have to go back and check if they had IR data and misinterpreted it. Yeah, I agree that if they had run an NMR, they would have known. I mean, sometimes you can explain away data. That's it. You know, as researchers, we become good at explaining away things that don't fit with our pet hypotheses. So I'd have to double check that to comment, but I speculate that they did it based on the elemental analysis and maybe a cursory look at the IR. Okay, with the remaining time, we're going to dive headlong into electron counting. Electron counting, this is a timely topic because if you're like me and you're knee deep in your taxes and you have to do your personal finance accounting, this is a form of accounting, but this is just organometallic accounting. This is electron counting. So we're going to go through this quickly. We have a handout that'll be, I think we didn't print it out, but it's available to you on Canvas, which has some of this information in a more organized way. So I didn't, if anything, we just go through quickly. I'd encourage you to review that handout. I'll introduce a couple concepts here, and then please stop and ask questions if anything's unclear. So the first one is this concept called the 18 electron rule. And Hartwig, in his textbook, he doesn't like that this is called a rule. He thinks it should be called the 18 electron empirical trend, but that doesn't seem as catchy to people. So that doesn't seem to be catching on. So this is what people call it, the 18 electron rule, but it's not a rule because it doesn't fall out of, it doesn't like fall out of the sky and all things follow this rule. It's as Hartwig fairly points out, an empirical trend. And that is that complexes, like that they're quote unquote happy, they're most stable when they have 18 electrons. And when they don't have 18 electrons, they are less happy, more reactive. And this is a direct parallel to what we see in the main group. And we know that in the main group, there's an octet rule, and that chemical entities that follow the octet rule tend to be stable, and those that don't follow the octet rule tend to be reactive. So if we think about methane, it's stable. If we think about boron trifluoride or boron trichloride, it is reactive because it does not have a closed octet around boron, at least. And the origin of the 18 electron rule is the same origin as its close cousin, the octet rule, which is that if you take a given principal quantum number, 3 and above, and then consider the next principal quantum number, you have 5d electrons, 5d orbitals, 1s orbital, 3p orbitals, each with 2 electrons. And if you do the quick math, that adds up to 18. So when you get to 18 electrons around your element of interest, you get to a stable structure. So let's take a case study of cobalt 0 and just see how this plays out. So if we think about the electronic configuration of cobalt 0, we start as our starting point with argon, and then just going left to right, filling up orbitals. We have we're going to donate into the 4s, 2 electrons. We're going to donate into the 3d, 7 electrons. And so that's the electronic configuration of cobalt in the gas phase. But when a complex forms, what happens is you have a ligand field around it. That ligand field you could think of as a defined electrical field that changes the relative stabilities of the orbitals involved. So once a complex forms, the 4s orbitals become destabilized relative to the 3d orbitals, and the 3d orbitals get filled up first. So instead of 4s2, 3d7, you have 4s0, 3d9. And we will then describe cobalt 0 as a D9 metal. What does it mean to be a D9 metal? You look at the periodic table, you count which column it's in, which group it's in. You'll get to 9, you'll find cobalt, that means D9. I make this point about 4s2, 3d7 versus 4s0, 3d9, because to me, when I was learning this, it was confusing. I would say everyone's referring to cobalt as D9 metal, but actually that doesn't seem to be its true electronic configuration of what's going on. So that's what's going on. Complex forms, the orbitals become lower energy than the s orbitals. That makes sense because s orbitals are spherical, and so they have they're destabilized by most ligand fields. And then that gets you your so-called D electron count. Why is D electron count important? We'll elaborate on that. So then that's the metal. Now let's talk about the ligands that we're going to put around the metal. These fall into generally 2 categories. So-called neutral donors, which are sometimes referred to as L-type ligands. They interact with the metal through a dative interaction. And there are anionic ligands, which also are referred to as X-type ligands that interact through the metal through a covalent interaction. Dative bonds, particularly in the older literature, are sometimes drawn using these arrows. Some more old school researchers adhere to this very rigorously, and so you'll see this still in the literature, but it kind of fell out of favor because you just have so many arrows around the metal. Sometimes it's like hard to see what's going on. This is not necessarily in favor now, but you will see this. And it doesn't mean anything special other than just that researcher made that stylistic choice to draw the data bond that way. So neutral donors are donors where when you dissociate them from the metal and you get them to a closed shell form, they are uncharged. So we're going to dissociate the ligand from the metal, we get it to a closed shell form, and it's uncharged. That means it's a neutral donor. So examples, we saw ammonia, it's one such example, phosphines, water, carbonyl. Olefins, we saw alkynes, arenes. Then there's the anionic donor. We already encountered some of these. We saw chloride, we saw CP, but this is a bit of a special case. So chloride, alkoxide, aryl groups and alkyl groups coordinated not through the pi system, but through a sigma bonding interaction, hydrides. X-type ligands, when you dissociate them from the metal and you get them to a closed shell form, they are charged. So think about chloride, you get it off the metal, you put 8 electrons around it, and you know that chloride then is negatively charged. Then there's this exotic third class that we won't cover except when we're trying to torture you in the homework set of difficult electron counting problems, which are called Z-type ligands. And Z-type ligands, they're like the friend who shows up to the party and they didn't bring any food or they didn't bring any drinks to share. They're kind of moochers in terms of electronic contribution to the party. They're just Lewis acids. They have this fancy name Z-type. These are Lewis acids. So these are things like we talked about trialkyl aluminums or boron reagents. They don't bring any electrons in. They just have an unoccupied orbital, and they will sit on a filled d orbital on the metal and form a stabilizing Lewis acid, Lewis base interaction. And in terms of electron counting, you can mostly ignore it. Okay, so we've talked about some general features of the metal. We talked about the types of ligands. How are we going to use this information to determine oxidation state? So this is pretty simple. What we're going to do is disassemble the metal to the atomic form of the metal and then all of the ligands. And we're going to count up how many X-type ligands there are, and how many X-type ligands there are and how much charge they carry will define the oxidation state of the metal. I think a lot of this, I will say in electron counting, it's a little bit confusing to discuss in the abstract. And the best way to learn it is to just do lots of practice problems. So that'll be the spirit that we do in this class. We won't spend too much time talking about the accounting principles. We'll learn from doing. One point I want to comment on in oxidation state is that it is in a formalism. It doesn't always reflect reality, meaning the physical oxidation state of the metal. And in fact, Pauling's postulate of electroneutrality states that in a stable complex, stable molecule, no atoms involved can have actual charge that's greater than +1 or -1. And that kind of makes some sense intuitively. If you've got something that's super highly charged and it's somehow in a stable bonding interaction with something that's very negatively charged, that just doesn't seem like it would make sense physically. I won't go into more details about that, but I just want to draw your attention to the fact that in chemistry, we use lots of formalisms to help us with accounting, and this is one such formalism. So just because something is formally, zero oxidation state, it doesn't mean that it doesn't react more like something that's in the +2 oxidation state or the -2 oxidation state. You need to consider everything in context. So we talked about d-electron count of the metallic forms of the metal, but now we have this detail of oxidation state. So when we're considering a complex, what we're going to do is we're going to look at it. We're going to determine its group number. That's the 0 oxidation state, d-electron count. We're going to subtract the formal oxidation state after adjusting for the ligand environment and any overall charge that the complex is carrying. And then that is going to be our d-electron count. And the d-electron count, what that actually denotes and physically is kind of interesting to think about. One can think of it as the formal definition here is the number of valence electrons in orbitals of predominantly metal character. And so you can think of these as the lone pairs, so to speak, that are around the metal. So I would just draw an analogy to the main group. In the main group, we're familiar with things like tertiary amines, just drawing generic tertiary amine here, and not doing it very successfully. And we know that when we draw this, implicitly, there's a lone pair that is on nitrogen. And you can think of an analogy here where the d-electron count, there's that many lone pairs, so to speak, or the corresponding number of lone pairs around the metal. Why is that important? Because for some elementary steps, you need quasi-lone pairs on the metal to be able to do chemistry, to give up electrons, for example. And then there's this overall electron count. So you have d-electron counts. Each of the ligands that's involved in a bonding interaction is going to bring 2 electrons each to the party. So you sum the d-electron count, you sum the number of ligands, and that gets you to the overall electron count. And when that's 18, that makes a stable complex. So let's do an example. Again, I think a lot of this is confusing to discuss in the abstract, but actually not that confusing when you just do it. So we'll take a complex that you've maybe encountered before, palladium dichloride bicacetonitrile. And let's do this exercise. So you have palladium. So we've dissociated all the ligands. I got a little ahead of myself here. We put them all in their closed state form. So we've got chloride. To get in closed shell form, it's got to be minus charged. We've got 2 of them. Acetonitrile, closed shell form, it's neutral. We got 2 of them. There are 2, it's over, the ligand environment is overall -2. That means because the complex is charge neutral, we need palladium to be +2. So we can then, palladium is in the group 10. So if it's +2 oxidation state, it means it's got 2 fewer electrons. That means it's D8. Palladium's bringing 8 d electrons to the party. We've got 4 ligands, each of which is bringing 2 electrons to the party. So let's do this. Maybe I'll just draw this out. I heard somebody whisper it. So palladium 0 is D10. Palladium 2 is D8. We've got 4 ligands. each bringing 2 electrons is 8 electrons. And so we need to add D8 plus 16 plus 8 electrons from the ligand. That gives us to an overall electron count of 16 electrons. Another term that we'll define below, but I'll just do this here, is coordination number. In the simplest form, coordination number just means the number of ligands around the metal when all of those ligands are monodentate. So in this case, the coordination number is 4. So a lot of times, standard electron counting problems are exactly this format. You get a complex and we ask d electron count, overall electron count, coordination number. So that's what we've got here. Simple case, but hopefully one that illustrates the general principle. So any questions on that? There are 2, I'll just add as a note, there are 2 different approaches that people in the field use for electron counting. One is called the ionic method and the other is called the covalent method. And in this class, I will only teach the ionic method, but both are totally viable. If you have already in a previous class learned the covalent method, then good for you, use that. The only difference really at a high level is in each of these bonds, you need to ask, where are the electrons? Are the electrons living on the metal? Are the electrons living on the ligand? When we break the bond, where do we put them? And so in the ionic method, we prioritize upon breaking up the complex, getting to closed shell species, and then thinking about whether they're charged or not. In the covalent method, you always break homolytically to get, excuse me, let me say that again. You always break the bonds to get charge neutral complexes, even when they're open shell. And then you can imagine that the math is just different. It depends, you're redefining who's bringing electrons to the party. Again, both are valid. Just don't, you cannot mix and match. You will find if you mix and match, you will get to crazy electron counts. So don't do that. And the reason I prefer the ionic method is because I think it is a little more intuitive because it maps better with the way ligands actually dissociate and reassociate in the context of catalysis. Okay, so we mentioned this term of coordination number. With monodentate ligands, very simple, it's just the number of ligands around the metal. But there are ligands we've already seen, like in the case of ferrocene, where that might not be the whole story. So the generalized version and the version that we're going to use in this class, and you might have learned different things in different classes, I'm just telling you what we're going to use in this class, is the number of electron pairs involved in metal ligand bonding. And for polyhaptic ligands, then that is different than the number of ligands. So let's look at some examples. Zeise's salt. This is a simple one. Coordination number 4. I think everybody would agree with that. Here's the more interesting case. So we've got ferrocene. So how do we think of ferrocene? We draw it, if we were to just dissociate it, we'd have this weird looking cyclopentadienyl anion, and it would be not immediately intuitive how to count this. So I like to break it up into the non-resonance delocalized form. And then it's easy, then it becomes easier to define, okay, what is this bonding interaction really depicted of? You've got a one olefin effectively here, another olefin here. These are each L type, so we would describe that as 2L. And then you've got effectively a Grignard here. It's an alkyl metal. So this is equivalent to a carbon, an alkyl metal bond. So, and we know that alkyl metal bonds, from what we described above, are X type. So that's the X contribution. Let me color code this NMR. clear way. So those are the X, these are the 2L. And so the overall way we describe this is a 2L, 1X ligand. See, this ligand is kind of like 3 ligands in one. It's 2L ligands and 1X ligand. And each of them is bringing an electron pair in terms of bonding. So you've got 3 electron pairs per CP, 2 CPs. That gets you to a coordination number of 6. Now, in other classes, people may have taught you other things like the number of atoms interacting with the metal. In that case, the coordination number of ferrocene would be 10. If you're just doing this definition of number of ligands and the coordination number of 2. So coordination number is not especially useful, but I kind of like this electron pair definition because it gets you to reasonable seeming numbers, like typically between 2 and 6. Okay. Basically out of time here. So let me let me go through one more topic, and then quickly we'll do like one. Yeah, let me just cover this, and then we can we'll pick up where we left off. So hapticity, we mentioned this a couple times. I think this is important to cover before we wrap up. Different groups, depending on their proclivities that in that environment, can interact in different ways to the metal. So let's take the case of a metal benzyl molecule. Then this can coordinate in this flavor, which we call eta-1, or it can coordinate through 3 contiguous atoms analogous to an allele, and that would be called eta-3. So one way to depict this eta-3 interaction, again, it's got, you can kind of think of it as like, it's got a olefin component and it's got an alkyl component. I don't know if this is helpful or more confusing way to think about it. And then in terms of the electron counting, when it's eta-1, 2 electrons minus 1, X type, coordination number 1. When it's eta-3, 4 electron minus 1, LX. So the key point is that in the context of catalysis, these haptotropic shifts can open up coordination sites around the metal. Okay, I think we're out of time, so we'll wrap things up there, and then we'll just pick up where we left off next time, wrap up electron counting, and then it'll be on to periodic trends. Any questions for me or for the TAs before we dismiss for the weekend? All right, thanks everybody. See you next week.